There's no order. GG. Well, yeah.
Thank you, Ed. Good evening to the club. I'm going to talk about CW, but also just electromagnetism and what that means to radio. So hopefully we'll all get something out of it. I always learn something during the research, and I can provide some of that information here too. So anyway, I'm Norm, AB6ET. I've been a ham for a while. I've been a member of this club for a while too, on and off over the years, but quite a while recently. So anyway, good club, nice turnout, good to see everybody. I know we're on TV also, so I'm glad that we are so active and doing so many things, all the different activities, the meetings, the fun things that are going on, the licensing. What a very good club. And I know that John sees them all, and he always visits with us. So that's something to say. So let's get started here and talk about a few things tonight. We're going to talk about the communications and electromagnetism and electromagnetic radio. So it's a brief history of wired to wireless, not necessarily CW, but certainly it's a big part of it. We'll talk about that in telegraph too. So this, of course, is me. In case there was any question about that.
That's the important slide.
So how did this turn into this? Telephone, telegraph, radio, Marconi and his wireless set. How did that happen? A lot of it's magic. But it's about communications, and man, us people have always wanted to communicate. It's also taken us to the moon and other places too. The electromagnetism that we're going to talk about. But we've always communicated, wanted to communicate. Ancient signaling here with smoke signals, this crazy thing where they flip these rods around and pull the wires and things. Oh, there's been light with the heliograph, noise, sound, drums, things like that, and flags. But communications, with all these different things, have some limitations. Day and night, distance, weather, and they're very slow too. One goes to the next, to the next, to the next, and can take a while. So there's got to be a better way. Everybody's always thinking of a better way. And one of the guys that was instrumental in this, Benjamin Franklin. We all know him from his kite experiments with the clouds and the lightning and all that. Well, he actually really did that. Some of it's, what we think of as the key and all that. I mean, he did that, but it wasn't getting shocked like he did. But anyway, what he did though was determine that everything is charged. There's positive and negative charge. He said there are positive and negative charge. Everything is charged. He thought that the positive was where everything came from. And we know now that actually negative goes to positive, but we fool ourselves into thinking that, okay, yeah, positive. But anyway, he started that. We keep up his myth that everything comes from positive. It really comes from negative going to positive. Right? Any disagreement on that one? I know there's rocket science in here. All right. One of the things that started electricity and electric for us was when around 1800, Alessandro Volta. There are a lot of names that you may hear. Volta, get it? Volta. Anyway, he developed this thing called the electric pile, and it made a continuous current. This created continuous current. They could make sparks and some other things with such things as a Leyden jar that would hold the charge but discharge. With this, you could create a current that would continue and make it flow. So he's one of the ones that started this. Now for us, this is real important. This man, Joseph Henry, experimented with electromagnets. in, maybe 18, 20, 30, something like that. There were electromagnets, but they were very weak. The turns were just a few turns wrapped around a bar. Well, he said, I will wrap many turns insulated around a bar and see what happens. Well, he kept wrapping and wrapping and wrapping, and he finally developed an electromagnet that would even just lift hundreds of pounds. So the electromagnet then became very important and quite interesting to a lot of people. You may know him. He went on later to be the first director of the Smithsonian. He also invented a thing because he's trying to make distant electromagnets. He invented a thing called a relay. So wires, resistance, all that sort of thing were not real good at the time, and they would only go a short distance. So he made a relay that would let a current go to another switch. The switch would close, another battery would go into the circuit, go on to the next and the next and the next, and eventually it would get to where you want to go. That's important to remember. Let me go back to Benjamin Franklin again. He was very influential in science and things like that. He went to France. He was the toast of the town. They called him a real dilettante. Anyway, he went back and forth to France many times. That would come into play in just a minute. So shortly after Henry is working, remember Henry from inductance? Shortly after Henry was working on an electromagnet, Samuel F.B., which Finley, Breeze, Morse, was able to put some of this to use. Samuel Morse was a painter. He was a portrait painter, and he was actually pretty well known. As a young man, in the early 1800s, he traveled back and forth to Europe. He went to Europe many times. And he, on one of his trips coming back, he struck up a conversation with somebody about electromagnets, and it really struck him as quite interesting. So he said, I'm going to look into this a little bit. Remember, Henry had already done much of this. So there's a lot of controversy about where electromagnets and all this sort of thing came into play. Anyway, let's just say Samuel Morse used this information. Henry did not license or patent his relay or the electromagnet. So Samuel Morse, going back and forth to Europe anyway, he's strikes up this conversation about electromagnets. Very interesting. What happened to him was in 1825, he was commissioned to go to Washington, D.C. He lived in New York. Went to Washington, D.C. to paint a portrait of the Marquis de Lafayette. The Marquis de Lafayette was very important in the American Civil War, or the American Revolution, in that he came over to command the troops, won a number of battles, and was really quite famous. And that is because France was very friendly to the United States, because Benjamin Franklin had been there before and they loved him. And so when the American Revolution took place, they thought that was a good cause. So Samuel Morse was commissioned to do this portrait of Lafayette while he's doing a tour of the United States. And he was invited over here by President James Monroe. So he's in 1825, he's in Washington, D.C., and he gets tragic news that his wife has died. And from Washington, D.C. to New York, where he lived, is a couple of days horse ride to get there. So by the time he gets the information, a couple of days, he gets back up there, a couple more days, she's dead and buried. He said, there's got to be a better way. And so he's thinking, got to be a better way. And he remembers some of these experiments that were done by Henry not too long before that. He gets together with this other experimenter and kind of not electrician, but he's a builder. He's a mechanical guy, does all kinds of stuff. Alfred Vail. Alfred Vail is also kind of rich because his family's rich, which Morse needed at the time because he got these wild ideas to make some things. So he gets together with Alfred Vail and says, I need this and this and this, and what are we going to do here? So Alfred Vail comes up with a couple of ideas. One of them is to do this. He creates a code. This is American Morse code. We use international Morse code now, but came up with this American Morse code. And he also built this. This is a replica of his key, and they still call it a key. It was called a key then. They call it a key now. So that was Alfred Vail made that. And this thing here is what they were using to do the original teletype or telegraph back and forth. And that is a paper tape wound on this clockwork here, and then electromagnets would put a mark on this tape as it went by. So they would have to then, it would put a mark on this tape. They would have to then take the tape off to look at that code that he just showed us here a minute ago. So you see a couple of lines and marks. And then he would go back up here and say, oh yeah, a couple of lines and marks. That's an A, and it's a D, and it's an I, and so on. And it worked. It worked. It was kind of slow, but it worked. Anyway, this was the recorder, or the clockwork thing with the paper tape. You can see the paper tape up here wound on this little reel. So Samuel Morse has got this idea. He said, I am going to get the government to buy this thing. He gets a friend who's a congressman who proposed to the government that they need this communications. And he says, I can do it. And he got I don't know if it was a grant or a commission to make a telegraph. And he's going to demonstrate it. Here's the telegraph relay. Here's that relay circuit we were talking about, one after the other. So in 1844, Samuel Morse is in Baltimore, and Alfred Vail is in Washington, D.C., and they send a message, wireless, or not wireless, by wire, using those things I just showed you. It's about 40 miles, something like that. Nothing like this had ever been done before. And they actually loved it. So they said, we need more of these things. Let's see what we can do. So Morse starts building some of these things, and he needs operators. These operators then are watching this thing as it clicks, and the tape is going by. And after a while, they don't need the paper. They know what the clicks are, and they say, we don't need the paper. When it clicks, I know what the letter is. I just write it down. So after a short while, they stop with that recording thing and the paper tape. They just listen to it by sound. Here's what the first message was on a paper. And you can't quite see it, but there's little lines here. This is what was marked on the paper. And as the tape went by, then they came back and wrote the letters later. W-H-A-T, H-A-T-H, G-O-D, and we know the message is what hath God wrought. And that message was proposed by the daughter of congressman or somebody. Said, oh, what should we send? Well, let's send that. And that was the message that was sent. So you can kind of see those little marks there, but that's what they were doing and using that. But here's what we came up with, these things. And here we have an electric sounder. These are electromagnets. These are the clicker. This bar here is like a bell, resonates against a stand that is off the board. And so when an electric current is put in here, this thing pulls up and down, and it clicks and makes the sound. I have some demonstration things here. In a few minutes, we'll get them out. But I have one here that our friend Phil just gave me tonight. And this was some of his original equipment, maybe not the sounder, but the key was. But, anyway, this is what that looks like right there.
Yeah.
Sure does. Okay, well, anyway, I've got another one here that's all connected up. We'll look at it in a few minutes. But so by listening to those clicks, these operators could determine what the letters were. This idea took off like crazy. And the country was new, so that was like 1844, 1849, 1848, gold was discovered, 1849, California is a state. And communications back and forth took months for a ship to go around the Horn or to travel across land, which was very dangerous. There were no railroads at that time that would go all the way. You could get up to maybe Mississippi River, but you couldn't get past there. We needed communications, and this Morse device was one that would look like it would fill the bill. Now, Morse was a United States inventor, but concurrently in England and other places, the telegraphs were also being used, and they were using a variety of things. Some of the ideas were similar, some were different. Many of them used multiple wires. You push a button, and one of these signals would go out, and you would do something on the other end. But you need a lot of wires, and there were moving magnets with arrows and things like a little compass would point to things. Kind of cumbersome, not always the best, but the thing that was real important about the Morse device was that it was single wire. So you could use two wires, one out and turn or grounded somehow. But they called it single wire telegraph, and that was very important. Anyway, we needed communications, especially out west. And 1849, telegraph companies were springing up everywhere. There were hundreds, maybe thousands of miles of wire all over the east. They needed something to get out to the west. Communication was kind of slow. 1861, we've heard about the Pony Express. Here's the Pony Express rider riding right next to the telegraph pole. Pony Express was in business for about a year and a half. Now it put them out of business. As soon as the wire went up, you don't need the Pony Express, right? Because all the information can go across there. Everything was getting sent by telegraph. Newspapers, letters, information, everything you could think of, commerce, business, it was just everything that had to be done was going by telegraph. So 1861, first transcontinental telegraph, 1861, Pony Express, short time later, they're out of business. But the improved technology of the telegraph was shown to be very valuable. Not too long after that, by the way, the Transcontinental Railroad hadn't been put in yet. It was proposed, but it hadn't gone in yet. Civil War, U.S. Civil War interrupted much of that. The Civil War also found another use for the telegraph. Abraham Lincoln was trying to communicate with his battlefield commanders because up till that time, Army generals and other commanders just given a general order at some time, like sure to win the war, and they went off on their own and never saw them again. Well, here now with the telegraph and these hasty offices being set up, Abraham Lincoln could communicate directly with his commanders in the field, and it proved to be very useful. He found out some commanders were not so good, others were much better, and he was able to provide intelligence and information to the battlefield commanders, saying, hey, watch out for these guys are coming that way, or don't go there, and so on. Originally, Abraham Lincoln would say, I need to send a telegram. He'd write it out, give it to somebody, they'd go down the street to the Western Union office and put it in the pile of messages to be sent out, and eventually it would go. That didn't come to be too well, to work out too well. So the government had to have its own system, and they took over many of the telegraph lines and also provided their own government telegraph service. And Abraham Lincoln became more and more active with the Civil War, and he was at the telegraph office a lot more than he was anyplace else, watching results, making decisions, and doing things. So after the Civil War, the Transcontinental Railroad picked up again, and where the railroad went, the telegraph went. And 1869, Transcontinental Railroad was in place, and the telegraph went with it. So now the country was linked by both telegraph and means of transportation. This is what a telegraph office would look like. Awful lot of ladies working here, and it was just a busy, bustling place. Things going on everywhere. At the local station, like at the train station, the agents there might be 2 or 3 agents at a time, but where all the telegrams would come in and out would be at a place like this. Also, undersea cables were being put into place all over. Here's one that went back and forth to America. They were going back and forth to England and the continent. And one that went to South America. And all over Europe was being wired too. All this was happening at the same time it was happening here, happening there. And these transatlantic cables were very important. Remember I told you about that American Morse that we had a little while ago? That was meant for the English alphabet. There's 26 letters, 10 numbers. But in Europe, there's a lot of different languages, foreign languages, different letters, different combinations. It didn't quite work for them. So another Morse language was developed, and very similar, many of the same characters and letters, but there were a few additions to it, and that eventually became known as Continental Morse. And it was a little more useful. In fact, everybody went to that many years later, but American Morse was still in use in the United States, but other parts of the world and these transatlantic cables or these other cables all use the international Morse, or continental Morse is what they call it. Here's some of the items that we were just talking about. Here's a sounder. This is a mainline sounder. It has a different sound to it, little different power rating. Here's a steel lever key. I have some artifacts here that we'll take a look at maybe in a few minutes if we have a few minutes. Steel lever key was very important because the keys originally were brass keys, maybe kind of. Sometimes they bend, you get kind of weak. The invention of the steel lever key was very important. Here's one that you might find at a home or a place of business with a key on the board. It's already got a key, it's got a sounder, everything is right there, all in one unit. I have one of those here we can take a look at also. I have one of those relays that we talked about. Okay, here's a steel lever key with a bug lid. A bug is a semi-automatic key, so that when you press it one way or the other, it makes continuous contact. You press it the other way, it makes vibrating hits, and you press it and you go hit. You only need 5 at a time, so I need more than that. You don't really need, but it really revolutionized Morse code sending, because it should get up to maybe 20 words a minute or so, and you do that for a long time. If you're not doing it quite right, you get repetitive motion. We call it carpal tunnel. You get something like that. One of these bugs. We'll look at one in a few minutes. it takes a lot of that stress off. Now these, a key would be bolted down to the table, but an operator would have a bug and he'd come in and use his bug and put this thing in it, a bug wedge, squeeze it up under there or between the contacts. And then when it's finished at the end of the day, you can pull it into the computer. So here's a bug. This is an old one. I have one that's a little newer. We'll take a look at. But anyway, you can see the vibrating thing here. This goes back and forth. The weight is the pendulum. So you press it, and then you press it the other way. It just makes a solid contact. You would have to hold it to make the longer dashes. And the telegraph also led to these things here: the cave, teleprayer. A lot of things were being used, with the same technology. Telephone also came into play at that time. Wires, all these things going all over the place. Okay, now here's where we get a little bit interesting. Michael Faraday, you've heard that term, Faraday, thought that doing a lot of electrical experiments, he said, if I put these wires next to one another, they I can charge one wire, and with the help of nothing in between, the charge goes to the other wire. And he started experimenting with that. He goes, that's kind of, we called that inductance. Later on, this man, James Maxwell, around 1850 or 55, something like that, he thought this magnetism, electromagnetism, and light were all part of the same thing, and they were waves. He developed some equations, and people know them now. Electronics guys know these as Maxwell's equations. And he said that everything is a wave, it's just at a different frequency. And that will play a part when we start looking at how this electromagnetism turned into a wireless radio. So the wires were everywhere. And you've seen pictures of those, thousands of wires. But you needed wire, you needed these stations, you needed relays, you needed all these in between operators, you need a lot of things. What if you had something that would just go from one place to the next without wires? Mm-hmm. Well, here's Heinrich Hertz. You've heard of Hertz before, right? Okay. Around 1890 or so, he had a coil that he could charge up. And he had another little coil near there. He would charge up this big coil and use something like a Leyden jar, discharge that into this coil, and he could hold this other wire or this other little coil. The thing would spark there, and it would spark here with him. He said, wow, that's very interesting. He thought it was useless, so he didn't pursue it too much. But he died a short time after that. And another young guy named Marconi, who was an Irish Italian, said, this is interesting. I'm going to start looking into that. So Marconi was looking at these Hertz, they call them Hertzian waves, these Hertzian waves and the things that he was doing, but there was no distance. It's just from here to there. It's a good idea, but how's it going to work? Right around the same time, you've heard of this guy, Nikola Tesla was also working on trying to transmit electricity through the sky, and he developed a coil that was essentially a step-up transformer that he could charge a small coil that had a big coil wrapped around it, and it would increase the power for this thing to jump, for this Hertzian wave or whatever you call it, to jump some great distance. Well, Marconi took this idea. The father of a successful invention has, a successful invention has many fathers, and a a bad invention, it's an orphan, right? Heard that? Well, there's some of that going on here with all these people. But anyway, Marconi took that idea here. Here's a this coil, one coil with another coil, and the generator and some other things created by adding a wire to it, a way to make these not sparks necessarily, but this field jump from one place to another at long distance. That's what he did. He's experimenting. In 1901, he claimed, I think he still say that he did, he claimed that he set up a station in Cape Cod, another in Cornwall, England, and was able to receive a signal back and forth. And they're not talking, they're using on and off Morse code. That's the tie-in with the Morse code. So Morse code lasted a good long time. There was some talking came in later, but in the meantime, everything was all by on and off Morse code. This is one of his or not, but anyway, this is what a spark station would look like. Big generator, some different radios, all these coils here to tune to a frequency, and oh man, all kinds of stuff. They needed a lot of power. They operated it in the area of around, and they thought this was the best place to be, around what we call 500 kc, 500 kilohertz. Now, below the broadcast band, below the AM broadcast band, they thought that's where radio worked the best. So you needed giant coils, giant antennas to make that work. For us, that's well below 160 meters, below the AM broadcast band. And that's where all the radio activity was. So these spark stations started coming up. Everybody more or less on the same frequency. They could tune these big coils, to a certain frequency, but when the spark came on, that thing was across the whole band. But each one had its own sound. Like we can recognize, different tones and sound. Well, these sparks, each one had a different sounding tone to it also. So they could more or less operate kind of on the same frequency, but they sounded different. We know about this. 1912, the Titanic. They had a radio operator, Marconi operators, and Marconi was making radios, providing radio operators, and then they would put them on these ships. So it's the White Star Line, Titanic. So the actual radio operators on Titanic were Marconi operating Marconi radios. Titanic call sign, who knows it? MGY. That right, M for Marconi, that's there, and GY for that ship. So there were some other radio companies, Telefunken and some others, but anyway, the Marconi stations were pretty popular, very, very powerful, huge facilities to make them work. Anyway, they sent out a distress signal, and not everybody was on duty, and they came back and forth. A lot of things changed after this. Here's what the radio room would have looked like. I don't know if this is the actual Titanic or maybe it's the Britannic, but this might be the Titanic, but they were essentially the same. The radio station would be here. Here's the key. There's actually two of them there. The keys, we'll see a picture of that in just a moment. All kinds of power distribution boxes. On the other side of this wall, you can't see it here, there's another whole room with giant generators in there that made the power to make this thing work. Oh yeah, here's the key right here. They call this the guillotine key. This key here would close and make the circuit. If the system took off or went crazy, they could pull that up and stop the circuit. Anyway, looks more or less like a key that we know now. Lever, the contacts, and the thing going up and down. And this knob here, like this, you know where this is here, right? With the plate underneath. I know, but why, John?
To rest fingers.
Well, you can rest your fingers on there, but you don't want to have your fingers slip off. it's a good way to be
Protecting.
and getting
Oh.
blasted by thousands of volts and thousands of amps. This thing was going to town here. So that's what that's for. Anyway, that's the type of key that was on Titanic. So during that time, right after 1912, many reforms came into place. One, they did have 24-hour watch on the radio, always somebody on there, and the ships at sea had to monitor this frequency. More or less everybody on the same frequency, but they had to do that. Well, the Navy thought this was a great idea, and they're really taking advantage of wireless and radio. In WW1, the hams, and there were a bunch of amateurs there that were kicked off the air. And the Navy took control of everything. Now here's the WW1 Navy dreadnoughts, which are big battleships. Look at these antennas and these aerials, wires and things that they have on there. They thought it was very valuable. And you know who's interfering with them and bothering them a lot? The hams, right? And they call them hams because they call them ham operators because they weren't professional and they weren't government operators. They were a bunch of hams out there. And the Navy would have been happy to kick the hams off for good. And they tried the best they could to do that, but they kept the hams from getting back on the air until 1919, almost 1920, and after World War I. World War I did see a use of radios and a lot of communication. There's the field radio station. And here's a wired set, field telegraph. Something very similar to this was even used in World War II. Now, the big drawback for radio, or what we call radio, was the receiving. And the receivers at the time were kind of poor. They had a thing inside of a glass tube that had metal filings in it called a coherer. And if a signal was detected, it would go through this thing called a coherer, and these metal filings would clump together, and then a sound would come through, so you could hear it buzzing in your ear as the signal came through. But every once in a while, you had to tap this thing and loosen it up, and start over again. Some were automatic. They have a little thing, keep that thing moving. Edwin Armstrong, or Howard Armstrong, I think that's what he called himself, developed a receiver that was much more sensitive, and he used a new invention that we'll see here in just a moment. But he invented the regenerative receiver, and then shortly thereafter, the super heterodyne receiver revolutionized receiving totally. And what made that work was developments by John Fleming and Lee DeForest. And here's what they came up with. These glass tubes. Fleming was in English, and so he called his tube a valve, because that's what it does. Controls current in there. A two-circuit valve, 1904. He said, or he came up with this as a detector to eliminate that problem with that coherer. And then in 1906, Lee DeForest, in order to avoid getting patent problems with this, put another little piece of wire inside here, which we now call the grid, and made a three-triode, a three-conductor tube. And he found out that if you put a small current on that grid, it would amplify that on the plate, because of the current flowing from the cathode or the heater being controlled by the grid, and then off to the plate, could amplify those signals. Well, Armstrong took advantage of that, started making his regenerative radio, then actually after that, then his super heterodyne radio. And these were what some of the things look like. 1920s amateur station. This is still Spark, but with the new radios, Spark was on its way out. So this was very nice radio set, but just about obsolete. In WW2, here's a radio operator on B29. He's got his hands full with every kind of thing you could think of. Transmitters, receivers, here's a whole row of transmitters, receivers, and kind of switchings and all kinds of things like that. Here's a post-war amateur station. A lot of that surplus stuff, some of we just saw there a minute ago is here. The one like this. Here's a nice college receiver there. I know somebody has one of those. And I know they're over here. It is for sale. Oh, by the way, yeah. 51J4. Anyway, all that led to these things that we have now. The computers, the cell phone, internet, satellite, digital, microwave, telemetry, all these things, wireless, and all this crazy stuff going on. All thanks to these. So the last of the last things here, the last wired telegraph actually went into India in 1970. The last Morse commercial Coast Guard CW station went up there in 1999. We still celebrate that every year in July. The night of nights, the last night they were on there. And the Morse code was no longer required for ham licensing in 2007. Now, why do we do it? Why do we do it at all? Why do we do it?
Because it's fun.
It's fun. Yeah, Morse code is fun. It's a skill, and remember our heritage. Here's Samuel Morse, here with a portrait here, picture with his color printing gadget there. Did he invent the telegraph? He had a lot of patent fights for quite a long time. Concurrently in Europe and the United States, a lot of things were going on, but it did work. It did work. So let me show you a couple of historical artifacts if we've got a minute. Ed? Okay. Okay, here we go. So here, let me see if I can do this. Okay. Here, I've got one of the old keys. This is an original and a sounder connected to a battery. This is what you would have heard. That would have been Morse code. But operator, they could go much faster than that. Very fast. Here's a relay. So it kind of looks like a sounder, except it just has a switch here. So the current comes in here, pulls in the relay, goes on to the next one and the next. Put in a new battery, a new circuit, and it goes on next. That's this. Because the resistance and the wires, you couldn't get very far. So you can only go so far with the batteries and with the wires and things. So you'd have to put in a new circuit with a new battery and a new relay and things like that to move it on to the next and the next station. Here's the key on board that we talked about. There's a sounder with a key built right on the same thing. It'd be used at home or business or something like that, where you need a unit all together. And that led us up to other things like this. Remember, I told you about the bug. Here's a bug right here. A more modern bug, but they're all kind of the same. Here's the vibrating reed, and then there's the controls back here. Let's see if I can make that up very quickly. I used the bug for a while, and then went on to other things. But there we go. Okay, okay. So
Ah.
press this way. Makes the dashes. Go this way. Yeah.
Yeah.
Not really an adjustment. If I was going to use it, I would have it adjusted. But anyway, it goes back and forth.
Okay.
And that led to, of course, here's a modern key. We've all seen these, you know. Has it changed anything from this one? And here's you know what a lot of people use these days. It's something like this. That bug is a semi-automatic key. The bug was invented by Horace Martin around 1904, and he called it the Vibroflex bug. So that's where that comes from. Anyway, this is a fully automatic key. You need an electronic unit here with the you know the keyer and all that sort of thing in there to make it work. So anyway, press it one way, makes automatic dashes. Press it that way, makes automatic dits, and then by just combination of going back and forth like this, you save your hand all that repetitive motion of going up and down. So anyway, those are some historical artifacts, things to look at. Any quick questions here? Stu has one. Go ahead.
So just to clarify, during the days of wired telegraph, that was all direct, right?
Well, battery, yes.
Yeah.
Battery, yes.
So,
Battery.
was there any time that they utilized alternating current to get further distances or anything like that? Just a curious.
No, not that I know of. Because it's all battery. Generated were developed that would provide current, but those were used for different purposes, not for the teletype. And
That's not Edison.
oh, Thomas Edison, you know, Thomas Edison in later life, kind of hard of hearing, but he and his wife were telegraph operators in their younger days. And it was not uncommon for him and her to be seen tapping one another's hands like that, communicating back and forth.
Interesting.
There's another story about a couple of guys named Richard and Al. You heard about these guys, Richard and Al? Richard was a telegraph operator in Chicago. And one day a shipment of watches came in. And of course, you know, the railroad agent controlled all that stuff, you know, where and what, because everything comes into them. And nobody claimed the watches. And he sent back to the company and said, hey, you know, these watches came in, what do we do with these watches? Nothing, they're yours, get rid of them. So, okay, fine. So he gets on the telegraph and starts sending about, you know, messages out back and forth to, you know, friends and other operators. We sold all these watches. Well, he got another batch and sold them out too. And he needed, you know, somebody to help him with, you know, watchmaking and repair and things like that. So he got all this guy named Al. And together they get together and started, you know, putting these things together. People would, you know, say, hey, I want this, I want that. You may know them by another name, Richard Sears and Al Roebuck.
Robot.
Yeah.
Okay.
Okay. So anyway, those are some of the stories. Telegraph. And wireless. We're in wireless now. We can talk around the world. That's where it all comes from. You guys like these fellows I just showed you here. Anything else? Terry?
For the Vibroflex, it just solved the problem with purple tunnel.
Right, because yeah, you just rotate your hand back and forth rather than just pounding up and down.
Because the light, you know.
Yeah, with a hand key, you could pretty reliably send, you know, 20 words a minute or so. But you get faster than that, it gets kind of hard. But these bugs would do 20 words a minute just to start it, and they can go much faster than that. So good operators and good receivers could go much faster and really take advantage of the system. And yes, Martin, and then
on the site, Florida is on in the phone tray, which is like a, LA, LA back to the actually the folks like last year on that, yeah, big. cell, you can find these.
Right, yeah, batteries, right, yeah, battery, right, yeah, battery technology really improved.
The other thing I find interesting, well, minimum rate in electric technology. If we do the fact that the 18, 30, the action, you know, the economics that they need. And so there's.
Oh, it's they were, yeah. Thank you, ladies.
Yeah.
To everyone.
Chatwin. That would be, what would you consider the average speed of a professional telegraph operator back in turn of the?
Yeah, I don't know. I would say probably 20 words a minute at least, maybe more. They were sending a lot of messages. And at 20 words a minute, you know, if you've ever done CW, you think it's, you know, really fast, but actually it's not quite, but almost conversational. So if you just do it in practice with it, you'll get up to that.
You might want to mention one of the positive things about CW is the low power requirements
Oh, sure.
and over voice and so forth, which is why it's so.
CW is still very popular, yeah, and very low power will get you through for sometimes voice vote because of the fluctuations in the voice. And CW then doesn't have that, it's just on and off. And you can hear like those tones. Yeah, anything else? Anyway, okay, thanks for having me here.